S3 is for physics, input, process, and output devices. Within this section, we're looking at all three different types of devices, and there are elements of this section which are more National 4 and others which are more National 5. Throughout the show, I'll highlight which ones are which. Input devices. Electrical and electronic systems can be split into three parts: input, process, out. The input part detects or senses or takes in a type of energy. The process part processes electrical energy, and the output part gives out a useful type of energy. For example, this could be kinetic in the form of a motor or light in the form of an LED. These are all examples of input devices: switch, microphone, solar cell, light-dependent resistor, and a thermistor. The input device senses or takes in a useful energy to convert it to electrical energy or an electrical signal, then sent to the process. Examples: the switch. By pressing the switch, you're completing a circuit which allows electrical current to flow to the next part of the circuit. A microphone takes in sound energy and converts it into electrical energy. A photovoltaic or solar cell takes in light energy and converts it to electrical energy. An LDR, which is a light-dependent resistor, has a resistance value that's dependent on the level of light. A thermistor has a resistance value that's dependent on the temperature. We'll look at each of these input devices within other circuits as we go through. From practical work and/or research, you should be able to complete the following table. For each of the devices, you should be able to provide the symbol, the energy input, and a possible use. So the LDR is a light-dependent resistor. So we start off with the symbol for a resistor, but then to show it's light-dependent, we have arrows going in, which is our light. The energy input is light, and a possible use for an LDR, you could have street lamps which turn on automatically. You could also have security lights. A microphone is an input device that takes sound energy and converts it to electrical energy. So microphones can be used in a number of different sources, for example, PA or public address systems. The symbol for a microphone is a circle with a line underneath. And here are our terminals. A solar cell is just a cell that works when it's provided with light energy. So we start with the symbol for a cell, short line and a long line, and again we draw the arrows going in which show that it's dependent on light. Light energy is our input, and solar cells are used for providing electrical energy to houses. So we use for the production of energy. Switch, a very common symbol that you will have seen before. Now the input energy to the switch is quite difficult. You have to push a switch or close a switch. So we could say the input energy here is kinetic. Possible uses would be turning on a device. A thermistor is our temperature dependent resistor. So we start off with our resistor, and to show us a thermistor, we have a line. Sometimes we have a little t here as well. Energy input there is heat, and thermistors are used very commonly within thermostats. So a thermistor is an example of an input sensor. The resistance of the thermistor depends on the temperature or the heat energy. The greater the temperature, the lower the resistance, which we can remember with the acronym temperature up, resistance down, or TURD. Here is the symbol for the thermistor. As I said, sometimes you'll see it drawn and there'll be a little T here just to show temperature. Thermistors are often used as input sensors for more complex circuits. For example, here the thermistor is being used to divide the potential between two resistors. And then this would then be connected to a larger circuit, perhaps going to a thermostat or maybe a temperature control on a washing machine. In this circuit, when the temperature increases, the resistance of the thermistor will decrease. Temperature up, resistance down. This will make the output reading, well, it's a voltage divider, so the larger the resistance, the bigger the voltage is going to be. So that's going to make this decrease. In this circuit, when the temperature decreases, the resistance of the thermistor will then increase. Temperature up, resistance down. Temperature down, resistance up. That will make the output reading also increase. Input devices, LDRs. An LDR is an example of an input sensor. The resistance of the LDR, the light-dependent resistance, depends on light level. The greater the light level, the lower the resistance. It's useful to remember the acronym LDRS, light up, resistance down, similar to what we had for a thermistor. And the symbol for the LDR is shown below. It's a resistor with some light going into it. LDRs are often used as input sensors for more complex circuits, similar to our temperature sensors. So we see in this circuit, again, similar to what we saw with a thermistor, the LDR is being used to split the potential of a supply. In this circuit, when the light level increases, the resistance of the LDR, remember light up, resistance down. This will make the reading on the voltmeter V1 also decrease. Assuming that there's no change in the potential difference of the supply, the reading on voltmeter 2 must increase to compensate for the decrease in V1. A decrease in light level would have the opposite effect. Thermistors and LDRs. So here's an example. An LDR is used as a light sensor in an automatic soap dispenser. The circuit is shown below. So remember, light goes up, resistance goes down. What's going to happen to the light levels when you put your hand underneath the soap dispenser? The light level is going to decrease. As the light level goes down, the resistance goes up. As the resistance goes up, that means the current is going to decrease. So an LDR is used as a light sensor in an automatic soap dispenser as shown. When the LDR is uncovered, the reading on the ammeter is 2 milliamperes. Calculate the resistance of the LDR. Remember, M or milli means times 10 to the negative 3. Ohm's law, V is equal to IR. 5 is equal to 2 times 10 to the negative 3 times R, 5 being the supply voltage. The resistance is equal to 5 divided by 2 times 10 to the negative 3, which is equal to 2,500 ohms. A different question may ask us to work out the current given the resistance. Another one could maybe have a graph where we need to determine the value of resistance which is associated with a certain temperature. Example 2. The circuit below is used to monitor changes in the temperature of a liquid. The thermistor is fully immersed in the liquid. So here we have a thermistor that's connected across an ohm meter. So the ohm meter is going to measure the resistance of the thermistor as the temperature changes. You're asked to state what happens to the resistance of the ohm meter when the liquid cools. Remember, temperature down, resistance up. So that means the reading on the ohm meter is going to increase. Example 3. A thermistor is connected to a 6-volt supply as shown below. And here in the table, we're given values of temperature and the associated resistances. We're then asked to calculate the ammeter reading when the thermistor is placed in a beaker of water at 40 degrees C. So the piece of information that we need to keep hold of is the temperature is 40 degrees C and the resistance is 400 ohms. So here's our solution. Read the resistance value from the table, then apply Ohm's law. Remember, from the table, we saw that at a temperature of 40 degrees C, R was equal to 400 ohms. We already know the supply voltage, and that's equal to 6 volts. Now what we need to do is to apply the formula. V is equal to IR, 6 is equal to I times 400. I, the current, is equal to 6 divided by 400, which gives us 0.015 amperes. Another input device that you may not have come across before is the capacitor. A capacitor is a device that's used to store up electrical charge. And those of you moving on to higher, we look into the capacitors in much greater detail. For National 5, you must be able to state what the purpose of a capacitor is, and you may be required in a problem-solving situation to explain situations where you should be using a capacitor. As the capacitor stores up electrical charge, the potential difference across the capacitor increases. And that's because each of the charges that's being stored by the capacitor has a small amount of potential. A typical capacitor circuit is shown on the next slide. So here we have a supply voltage of 4.5 volts and a switch, a capacitor and a resistor. When the switch is closed, current is going to flow through the resistor, and the charges, that is the current, is going to start to get stored up on the capacitor itself. Now, as the charge is stored on the capacitor, the potential across the capacitor is going to get larger, which means the potential across the resistor is going to get smaller. So what we could do is we could connect the capacitor to some kind of device that needs a large amount of charge. We could attach this to, for example, an LED. When the capacitor reaches the correct voltage, the LED is going to turn on. But there will be a delay. So capacitors are quite often used for delayed circuits. The maximum potential difference, that is voltage, that can be reached by a capacitor is equal to the supply voltage. For the circuit shown, the maximum potential difference would be 4.5 volts, because 4.5 volts was the value of the supply. The capacitance, or the storage space in a capacitor, is measured in a unit called farads. And as stated before, capacitors are normally used where we want to have some kind of delay in action. So they're often used within timing circuits. In National 5, you're not going to be expected to perform calculations on a capacitor, but you should be able to state what its maximum voltage is going to be, what it could be used for, and of course the definition of what a capacitor is. That is a device that can store charge. So here is a circuit diagram showing some of the input devices that we've discussed. We're asked what happens when something changes. And that's typical of this type of question. Normally we have some kind of environmental factor that's changing, and we need to state what's going to change because of that. So let's identify some of the components. At the very, very top here, we have our thermistor. Here we have our variable resistor. And as we'll look at later on, the output devices, this, which you may be familiar with already, is an LED. And for the process devices, this one here is a transistor, which is just an electronic kind of switch. So if enough potential is across the transistor is going to switch on, current's going to flow to the LED, and the LED is going to turn on. The transistor is connected in parallel with the variable resistor. So whatever the value of voltage across the variable resistor will have the same value of voltage across the transistor. So let's read the question properly. The variable resistor is adjusted until the LED switches off. The temperature of the thermistor is now increased. Temperature up. Maybe write that one down. T is going up. The resistance of the thermistor decreases as the temperature increases. So that goes along with our rule, temperature up, resistance down. Which row in the table describes the effect of this change on the voltage across the thermistor, the voltage across the variable resistor, and whether the LED stays off or switches on? Well, let's have a think here. This is a series circuit. So if the temperature is going to increase, we're told that the resistance decreases. So the resistance of the thermistor is going to decrease. Remember from previous slides, if the resistance decreases, then that means the voltage is going to decrease also. So the temperature goes up, resistance of the thermistor goes down, the voltage across the thermistor is also going to go down. But because this is a series circuit, if the voltage across the thermistor goes down, that means the voltage across the variable resistor must go up, because those two things, the voltage across the transistor and the voltage across the resistor, must add up to the supply. Vt plus Vr is equal to Vs. So as the voltage across the thermistor goes down, the voltage across the resistance must increase. So let's have a look at our table and see if we can start to identify some. So we know the voltage across the thermistor decreases, so that's right, that's right, that's right, that's wrong, that's wrong. The voltage across the variable resistor is going to increase because the voltage across the thermistor is decreasing. So that's right, that's wrong, that's wrong, that's wrong, that's right. Now if the voltage across the variable resistor is increasing, then the LED is going to switch on. So that's right, that's right, that's right. So the only one that has all three correct is A. So temperature goes up, resistance of the thermistor goes down. Voltage across the thermistor goes down. Voltage across the variable resistor goes up. Transistor switches on, LED is on. Now, when you're doing the analysis, it's quite useful to write this down in bullet points. But if you're asked to describe how the circuit operates in a National 5-unit assessment, you will be expected to write in sentences. So here would be our bullet points. So temperature goes up. Resistance of the thermistor goes down. Voltage across the thermistor goes down. Voltage across the variable resistor goes up. Voltage across a transistor is also going to go up. And the LED is on. And that's because at the point where the voltage across the transistor goes up, the transistor